my YouTube viewers. In this video, what we're going to do is we're going to forecast hurricanes with an ARIMA model. And basically, we're going to do that by writing a program in Python. So in order to write the program in Python, we need to import some libraries that will enable the program to run whenever you try to execute it. So the first thing that we're going to import is math, which is an inbuilt function in Python. And then we're going to import NumPy as NP, which is a numeric library that also creates NumPy arrays. We're going to import pandas as PD, which is a data processing library that also creates data frames and series. We're going to import matplotlib.pyplot as PLT, which is a visualization library. And from statsmodels.tsa.arima model, we're going to import ARIMA. So statsmodels is Python's statistical library. TSA is the time series analysis module in statsmodels. And ARIMA model is another model within time series analysis, and ARIMA is the function. And then from statsmodels.tsa.seasonal, we're going to import seasonal decompose. And so seasonal is a module within TSA, and seasonal decompose is a function in seasonal. So after we have imported our libraries, then what we're going to do is we're going to generate synthetic hurricane data for 30 years. So the first thing we want to do in that regard is we want to set our seed. And the reason why we set our seed is so that whenever we run the program, it will always initialize to the same values. So you set your seed by typing np.random.seed brackets 42. And then we define our years equals pd.daterange brackets start equals 1990, comma, periods equals 30, comma, frequency equals years. And then trend equals np.linespace brackets 5, comma, 10, comma, lin years. And so lin years is going to be 30. And so that's a gradual increase in hurricanes. Seasonality equals 2 times np.sine bracket 2 times np.pi times brackets years.here modulo 10 brackets divided by 10. So that's a decade-long cycle. Noise equals np.random.normal. Normal is a normal distribution. Brackets 0, 1, lin years. So that is a mean of 0, a standard deviation of 1, and a length of 30. So that's random noise that has been inserted. So hurricane counts equals trend plus seasonality plus noise. So now we're going to create a data frame that contains the hurricane data. Hurricane data equals pd.dataframe brackets, curly brackets, year, colon, years, comma, hurricane count, colon, hurricane count. And so what year is the first column and hurricane count is the second column. And now what we're going to do is we're going to set year to be the index of the data frame. So hurricane data dot set index brackets year, comma, in place equals true. So now what we're going to do after we have created our synthetic data and created the data frame, we're going to decompose the time series into trend, seasonality, and residuals. So decomposition equals seasonal decompose brackets hurricane data square brackets hurricane count square brackets comma model equals additive comma period equals 10. And then we plot the decomposition with decomposition.plot, and plt.subtitle hurricane count decomposition, font size equals 16, and then plt.show. So now we split the data into training and testing sets. So training is going to be for the first 25 years, and test is going to be for the last 5 years. So train data equals hurricane data, square brackets, hurricane count, square brackets, colon 25. Test data equals hurricane data, square brackets, hurricane count, square brackets, 25 colon. So now what we're going to do is we're going to calculate the PDQ. So if you have watched my previous videos, I talked about calculating the PDQ, and I have actually showed how to calculate the provided the code for calculating the PDQ in a previous video, but I decided to do it in this video here. And so what I've done is I'm just leaving. You can pause your video, and this is the code to actually calculate the PDQ. So at the moment it's commented out, and the reason why it's commented out is because it takes a long time to cycle through it. And so after you've cycled through it and got your order of your PDQ, then what you need to do is you need to comment it out so you can't use it again, because it just takes a long time to do it. But I've got the code here on the screen, so you can stop your screen, you can stop the video and copy the code if you want. So that's how to calculate the PDQ. And now we're going to define our model. So we're going to, ARIMA is your model. So model equals ARIMA brackets, train data, comma, order equals 6, 2, 7. And that's P is 6, D is 2, and Q is 7. And then model fit equals model.fit brackets. So now we're going to forecast the hurricane counts for the next 5 years. Forecast equals model fit dot forecast bracket steps equals then test data. And then forecast index equals test data dot index, and then you use the test data years for forecasting. So now we're going to plot our data onto a graph. So we're going to plot the observed and forecasted hurricane counts. plt.figure brackets fig size equals 6, 4. plt.plot brackets hurricane data.index, hurricane data brackets hurricane count, label equals observed counts, color equals blue, alpha equals 0.6. And then plt.plot brackets forecast index, forecast, label equals forecast counts, color equals orange, line style equals dash. And now we're going to put a vertical line in the chart. plt.axv line brackets x equals train data dot index square brackets -1, color equals gray, line style equals dash, label equals train test split. So, and then finally we're going to add labels, title, and legend to the graph. So the title is Hurricane Count Forecasting using ARIMA. The X label is here. The Y label is Hurricane Count. You get a legend and a grid, and now we're going to show it. So first thing that it shows is it shows the decomposition. So it shows the hurricane decomposition. So it shows the data, the hurricane data, shows the trend, shows the seasonal, and it shows the residual, which is the noise. And then so that has decomposed the hurricane data that we have created. And so now what we've done is we've got the hurricane count forecasting using ARIMA. So the blue is the observed counts, the orange is the forecasting counts, and the gray is the split between the observed counts and the forecasting counts. And as you can see, if you can see on the right hand side, the observed counts and the forecasted counts, you can see that the forecasted counts are very similar to the observed counts, and that's because we use the correct PDQ. If you don't use the correct PDQ, you're not going to get the correct forecast, and that's why you have to calculate the PDQ whenever you use the ARIMA model. And I know I haven't included the code to calculate the PDQ in every video that I have made, but it's important to, whenever you use the ARIMA model, to calculate the PDQ. And I did actually include the PDQ in this video. And you also have something called SARIMA, which has a seasonal element to it, and that the code is even longer, and it takes even longer to calculate these PDQ for these ceramics. So that's going to conclude this video, because I've covered the seasonal decomposition, and then I've covered the forecasting, and I'm giving you the code for the PDQ, so you can use that whenever you're working with the ARIMA model. And so the next video is going to be another statistical subject, and I hope you decide to watch it.